Hey there, welcome back to the Nauctis on YouTube. The evolution of the container ship has undergone a remarkable transformation since its inception in the 20th century. Initially conceived by Malcolm McLean, an American entrepreneur, the idea was to refine slow and costly loading and unloading process that had previously been in place. McLean invented a crate that could be moved from truck to ship without the need to unpack and extract its contents, the precursor of modern container transportation. In 1956, McLean and his company, Sealand Service, launched the first commercial container ship, the Ideal X. This innovation brought significant changes in cargo transport processes, and since then, the use of container ships has continued to grow and become industry standard. Now, we see another huge leap in the evolution of container ships with the launch of MV Yara Birkeland, the world's first autonomous electric container ship launched by Norwegian fertilizer company, Yara. The ship is designed as part of Norway's commitment to achieve a zero-emission vision by 2050. In a test conducted in November 2021, Yara Birkeland demonstrated its ability to load containers autonomously and was capable of carrying up to 100 containers. Interestingly, the ship can operate entirely without a human crew, relying solely on technology and computer systems. This development shows how far we have come in technology and innovation since the early days of container ships, and may provide clues about what is to come in the future of cargo transportation. Before the Yara Birkeland took to the seas, the ship model was tested in facilities to ensure the ship could operate correctly. In contrast to large-scale mass production such as motors or mobile phones, mega machines like ships require strict supervision at every point of construction, from the design stage to the launching of the ship. Designing and building a ship is a time-consuming and complex process. Various potential errors and inaccuracies are assessed from the early stages, with preventative measures and tests taken at each step. This is why ship model testing is crucial from the basic design stage of a yet-to-be-built ship. The significance of ship modeling can be explained by its name itself, where large objects like ships can be assessed in miniature scale, allowing visualization of ship behavior and other physical characteristics before the commencement of ship construction. Recently, the emergence of revolutionary ship design software and other simulation systems has eased the complexity of manual model testing operations to a considerable extent. However, the importance of physical model testing remains, as software-based approaches have their limitations and often rely on empirical relationships established through physical tests. Small-scale physical ship models provide a number of key advantages in simulating and analyzing the main parameters of the ship prototype, such as resistance calculations. However, their drawbacks include their inability to predict detailed design aspects, such as general layout and tank capacity, as well as responses in extreme open sea scenarios. Despite having a lower accuracy level compared to digital methods, ship model testing is still recognized as an essential early stage in ship design and research. Building a ship model is a task that requires precision and attention to detail. Modern CAD or TAM has simplified this process, yet aspects such as dimensions, hull shape, significant ratios, configuration, and center of gravity still need to be carefully considered. Ship models are usually not made from the same materials as the actual ship, like steel, for various reasons such as availability. practicality, and differing buoyancy to weight needs. Instead, commonly used materials include wood, wax or paraffin, FRP plastic, GRP or fiberglass, and light metals. The manufacturing process involves creating a negative model, or plug, which is then coated with a release material and shaped with layers of fiber soaked in resin. This mold can then be used to make as many required ship models as needed. Milling machines are used to ensure the accuracy of shape and hull lines. Making these ship models requires hydrostatic calculations before the production stage, and the precise completion of the model is very important, as small errors can have a major impact on the ship's design. High computing technology has simplified this process, enabling ship models to be made in a way similar to the construction of actual ships. Ship models are typically made to mimic certain types of ships, such as bulk carriers, tankers, and barges. However, simple models are also made for basic studies such as resistance calculations and propulsion. All scale model experiments are carried out in tanks or basins of fresh water with varying shapes and sizes. The towing tank is an experimental facility with the main function to calculate and resolve ship hydrodynamic problems. The towing tank was first introduced by William Froude in 1870. At that time, it was only used to measure resistance on ship models. These tanks resemble long pools, often as deep as 100 meters, their width usually dictated by the width of the ship model itself. This narrow freshwater channel facilitates a variety of experiments in which the model must move within a certain distance without significant cross-movement. These tests are crucial in determining a range of important parameters, such as resistance, propulsion, displacement measurements, propeller immersion, trim, speed, and engine performance. However, the narrowness of the towing tank restricts experiments that involve the ship's lateral movements. For maneuvers and specific tests that involve sea conditions, wider basins and flumes are employed rather than the narrow towing tank. These facilities are carefully designed with systems controlling temperature, humidity, air circulation, and other environmental conditions, as changes in water temperature could impact the results of the tests conducted. When the model is tested, it is placed in the towing tank. There, ship models are typically mounted on a carriage, a kind of moving platform that travels along rails on the side of the tank, moving synchronously with the model. This carriage not only supports the model, but also serves as a base for important recording instruments, computers, and other data collection systems. Researchers and observers can also board the carriage to witness the experiments firsthand. It's important to understand that models in towing tanks are also affected by the effects of shallow water and resistance. The models operate in highly restricted conditions due to the shallow water depth and narrow width of the tank. If the model is large, these constraints become increasingly critical. Changes in water flow caused by the model's close proximity to the physical boundaries around it, on the sides, affect the hydrodynamics of the floating body. Consequently, this increases resistance and disrupts the model's speed. This concept is easier to grasp when viewed from the perspective of the more complex ship hydrodynamics. Towing tank tests include calm water resistance, open water propeller test, and self-propulsion test. The calm water resistance test aims to determine the resistance needed by the ship model at specified speeds under calm water conditions. During this test, engineers will record the power on the ship model at each predetermined speed, allowing them to accurately predict the full-size ship's resistance at every speed. Then comes the open water propeller test, which is a test performed on the ship's propeller performance to obtain propeller efficiency. The purpose here is to maximize the thrust produced and reduce the fuel consumption needed to move the propeller. Propeller efficiency encompasses propeller design, rotational speed, and more. The propeller will be placed in a strout where there's a motor equipped with a dynamometer to measure torque and RPM at a specified speed. This testing assists in the selection and design of propellers to meet the requirements of the ship being constructed. Then there's the self-propulsion test, a test involving the combination of a ship model and propeller. The propeller is attached to the ship model and tested together. An electric motor and dynamometer are also attached to the ship model. In operation, this ship model and propeller are moved with the towing carriage at a predetermined speed. Ship model testing can also be performed in a facility called a wave basin. This facility differs from the towing tank in terms of its relatively larger width. The width and length are comparable in magnitude, but the depth remains more or less the same, around an average of 10 meters generally. The wave basin at the University of Iowa in the United States is one equipped with the most advanced equipment. The construction of this wave basin required an investment of $5 million US. Because of the wider dimensions here, the ship is not restricted in its 6 degrees of motion. Therefore, this physical pool is used to conduct seakeeping tests, such as roll decay, heave, or other maneuvering experiments like zigzag, spiral, or turning circles, which couldn't be achieved in the narrow towing tank. Seakeeping refers to a ship's ability to maintain stability and good performance when sailing on the open sea or in wavy sea conditions. The wave-making equipment in this facility can produce waves of varying heights according to the requirements. This site also features wave absorbers to dampen or eliminate waves after testing is complete. This setup differs from that of the towing tank. Here, the model is moved and rotated with the aid of an arm that reaches more than half the tank's distance. Wave creators and absorbers are always positioned opposite one another. At the University of Iowa's Wave Basin, the data obtained from these tests are used to develop computational fluid dynamics, or CFD software. With the evolution of this technology, conventional testing methods for models will become a thing of the past. Instead, testing will use 3D simulations, enabling more efficient and accurate testing processes. For even more realistic testing, ship models are tested in wave flumes. This test simulation is more realistic because the facility creates a testing environment for models that is akin to the actual sea conditions experienced by ships. Physically, flumes resemble towing tanks. Here, too, the length exceeds the width, which significantly surpasses the depth. Also, the depth is not much, although it could be more than that of a simple towing tank. Another interesting feature of flumes is the deep hole somewhere in the middle of its length. The depth of this hole is quite high and made for technical reason. The primary idea behind this is to create ocean topography, where there are various seabed depths, ranging from shallow depths to depths of around 10,000 feet or more. The unique feature of wave flumes is the wave generator. This system produces waves with varying wavelength, frequency, and of course, height. Now the question arises, how do we generate waves? The answer could be simple. With wind, by creating pressure variations and underwater disturbances, or mechanically. As wind and pressure variations and underwater disturbances are difficult to artificially create, mechanical means are the best way to go. Mechanical methods trigger hydraulic forces, which in turn do create waves in the tank. These wave makers are primarily driven through electric motors and can be costly to construct. The basic principle behind most wave makers is the movement of a hydraulic ram triggered by a servo motor that receives electrical or digital signals as input. That wraps up today's video. Don't forget to hit the like button and subscribe for more awesome videos. Catch you in the next one.